All right, so in this video, we're going to talk about pedigrees and how they can help us identify different genetic characteristics. So some of these characteristics are disorders, and that's what we're going to be talking about. But people use pedigrees to trace bloodlines for many animals that they are trying to sell so that they have this beautiful, perfect bloodline of some collie or something like that, right? We can use pedigrees also to help us identify what type of genetic disorder you're dealing with. Is it a dominant disorder? Is it a recessive disorder? So many different traits and disorders have genetic origins, and many of these follow Mendel's laws of dominance. And so these traits can be controlled by a single allele. And if they are, then they're easy to show on a pedigree. So if we have a single allele that is associated with a trait on a body cell or a body chromosome, so autosomal chromosomes are any chromosome other than your sex chromosomes, then we can use a pedigree to help us identify them. We can also do it with sex chromosomes, but that's a little different. So a pedigree is a chart of a family's history with regards to that specific trait that we care about. So this is done on many organisms. We typically use males as squares and females as circles. If an individual is affected with some type of a trait, then they are shaded. If they are not affected, then they are unshaded. And we can look at, family history to see if a disorder is dominant or recessive, or a characteristic is dominant or recessive. So we're looking at some pedigree for some characteristic. It doesn't matter what it is. Both mom here and dad are unaffected, but their child is affected. This tells you that this has to be an autosomal recessive characteristic. Okay, so if this is a disorder, it's an autosomal recessive disorder. Ooh. And so only, there we go, only people that have two lowercase letters are going to have whatever that characteristic is. And so here we're looking at some trait elicited by the letter A. All right, so in this case, if you have a big A something, you don't have that disorder. All right, so no disorder. But if you have two little a's, you have disorder. And so we see mom has whatever that disorder is. Mom and dad have two children. I'm sorry. They have this child here and this child here. Both of these children are unaffected. They're both heterozygous because they got one from mom, whatever it is. They each marry, and this person, their child, has one dominant, one recessive allele. Over here, she also married, and they had three children. We only know information about one because this child here is dominant recessive, and these two marry. So that's like a really, really close family relationship. Probably not acceptable in reality, because that's like your children, your children's children. So like first cousins, that's weird, but no bigs. We're just doing this for funsies to show you, right? So in the offspring, we have two that are homozygous recessive and one that is heterozygous, or that we don't know. We don't know if he's dominant or recessive. She's dominant or recessive because she hasn't had children of her own. So this also does show you the importance of inbreeding and why you should not do it. Because if this is a serious disorder, then the more inbred an organism is, the more likely they will show that disorder. Okay, so inbreeding is bad. Just FYI, not that you didn't know that already. So let's now look at my own little chart. And let's try and see if we can figure out what all of these individuals are. Okay, so we'll just use the same A's, right? We're using a big A, something for no disorder, and little a for disorder. So when you're doing this, the first thing you can do is you can go through and you can mark down everybody that is colored in as, since this is a recessive characteristic, this is a recessive pedigree. We can put down that this person's AA, this person's AA, and this person's AA. That's what we know. We also now know that both dad had a little a and mom had a little a because they produced this child and this child. So that means that they had to, since they don't have the disease, they had to have the dominant characteristics as well. Now, we can look at this side first. So this daughter marries a man, and this man doesn't have the allele. So we know he has one big A. We know that each of the children got a little a from mom. We also know that these two children don't have the disease, so they must have gotten a big A. But this child over here has the disease. That tells me that this dad is big A, little a. He's heterozygous for that characteristic, whatever it is. Over here, we know that this person doesn't have the disease. So this man doesn't have the disease. What we don't know is what his other characteristic is, because he could have a big A, little a, or a big A, big A. We don't know, so we put a line. He marries a woman who is big A. But again, we don't know what the other one is. And the reason we don't know it is because neither of their children have that, or their child doesn't have that disease. But they only had one, so they could be big A, little a each, and they could, one of them pass on a big A, one pass a little a. We don't know. We know that she marries a man, and he also doesn't have that characteristic, but we don't know what this is. And we do know that they have one child. That child doesn't have whatever that is. So all of these over here, we know they're either homozygous dominant or heterozygous. We know more on this side of the chart than this side, right? But at least we know that information. So if that didn't make sense to you, you definitely should come to my office hours, because I can talk you through it again, or I can help you with something else if you do understand this. My office hours are very boring when no one shows up. All right, I'm going to stop here, and we'll get into those recessive disorders in the next video.